There's an old movie called Amadeus. It's about Amadeus Mozart. And in it, there's a character by the name of Salieri. Both of these are historic figures. But Salieri was, in the movie anyways, secretly jealous of Amadeus because Salieri could recognize this guy was just genius. Like, wow, he's a big cut above me. And that's kind of the way I feel about some of the work in this section. I'm like, wow, whoever came up with stuff, hats off to you. This was just brilliant. And what we're going to do in this section is we're going to make certain trigonometric substitutions depending on the shape of our integral. Now, if your integral contains a term like this, where you have a number squared minus an x squared, then you can use this substitution. If your integral has something like this in it, then you got another substitution. Or finally, if you have an x squared minus an a squared, so that is the variable squared minus this, then you're going to have a substitution like this. So your job is going to be many-fold. You're going to have to recognize which substitution you're going to want to use. You're going to have to mold this or mold your problem to look like one of these. Make your substitution, and I don't know. It's just going to be pages and pages of work, and I envy you over the next 2 days going through this kind of stuff. It's going to be really, really fun. I'm sure you're going to be tweeting about it to your friends and stuff like that. But let's see what's going on with these things. And, you know, we'll try and take it slow. Maybe we'll do a couple more on Thursday as well. Thursday is going to be section 7.4 and review, but if we get some time, I wouldn't mind spending some more on these. So we'll start with example A. The integral of x cubed over the square root of x squared plus 9 dx. Now let's take a look at our trig substitutions here. What do these things look like? What's the closest thing we've got to this? What form does it fall into? So let me just write, I don't know, we'll do 1, 2, or 3. Which form is it looking closest to? 2. 2, because you've got a plus here, right? So the a is going to be really 3 squared, and then we've got an x squared term, so okay, looking pretty good. So we're going to let x equal 3 times the tangent of theta. Now let's figure out a couple things here. First of which is dx by d theta. You can look at your notes from the last section. What's the derivative here? Three secant squared of theta. And then, of course, we can rewrite this as dx equals 3 secant squared of theta d theta. So there's our substitution. It might also be helpful to keep around your substitutions from the last section again for other reasons. These identities are going to be really helpful in this section, in particular stuff like this, 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 and this. Those are the ones that you might want to have handy for the work in section 7.3. Let's see, what else we got here? Well, let me rewrite a couple of these things. Let's put these things in here. You know, before we do that though, let me do one more thing. And that is, we're going to need to set up a little triangle here. And the triangle we're going to set up relates to this. If I solved for tangent of theta, I would get tangent of theta equals x divided by 3. Let's set up a triangle that has this relationship here. So I'm just going to draw myself a right triangle. And in kind of keeping with my just-in-time delivery of review information, let's remind ourselves of something here. What's this SOHCAHTOA stuff all about? You guys have seen this a time or two, I'd imagine. What do we got going there? Sine is opposite over hypotenuse.
Cosine is adjacent over hypotenuse.
Keep going, James.
Tangent is opposite over hypotenuse, or adjacent. Sorry.
Yep, tangent's opposite over adjacent. Thank you. So I'm going to put a theta right here. And tangent, as James just gave us, is opposite over adjacent. So label a couple of these sides so that it has the opposite and adjacent in it. Jameson, what's that going to look like here? What am I going to label where? This side, this side, this side. I got the bottom, the vertical, and the hypotenuse. What should I label with what?
Well, 3 goes on the bottom, X on the right.
Nice. So 3 on the bottom, X on the right. Here's your opposite, here's your adjacent. Can anyone figure out what the hypotenuse would be?
Square root of x squared plus 9.
Awesome. Thank you, Clyde. Square root of this squared plus this squared, so x squared plus 9. Now that's a nice little double check of your work. If you chose the right trig substitution, then that square root term that you have in your integrand should pop out in your triangle. If it doesn't, there's a mistake. Go fix it now. Don't wait till later. All right? Okay. Let's continue with our trig substitutions. It's not till when we're all done that we're going to have to go back and figure out this kind of stuff. All right? But for now, let's make our substitutions. And that's going to get kind of messy here. So let me give myself a little more space, bring this down. It's going to be the integral. And let's see here. X is now 3 tangent of theta. So it's going to be 3 tangent of theta cubed. And then over here, I'm going to have the square root of x squared. So square root of 3 tangent of theta squared plus 9. And I guess I could shorten this a little bit. Times dx. Well, what's dx? Dx is 3 secant squared of theta d theta. So 3 secant squared of theta d theta. All right, so a lot of your trig substitutions coming your way still. But all I've done so far is just make the substitutions that were kind of recommended to us by the form of the problem. Now when I cube this out, 3 cubed is 27, times 3 again is 81. So let me in the numerator rewrite this as 81 tangent cubed of theta times secant squared of theta d theta. In the denominator, this is going to be 9 times the tangent squared of theta. So 9 tangent squared of theta plus 9. And that's looking okay. But here's the nice thing. In the denominator, I can factor out that 9. So this right here factors as 9 times the tangent square root of theta plus 1. Does that help at all? Mm-hmm. What does it do for us?
Gives you secant squared.
Yeah. That's one of your trig substitutions from the last section. That's going to be 9 times secant squared of theta. And when I take the square root of that, I'll get the denominator. So this becomes the integral of 81 tangent cubed of theta secant squared of theta d theta Square root of that is just going to be 3 secant of theta. 3 secant of theta. Whew. Wow. Can I do any simplification here? Yeah. The secant can cancel. The 3 can cancel. So I'll take a 27 out in front times the integral of tangent cubed of theta times secant of theta d theta. Whew. A lot going on there. Trying to slow down a little bit. Are we okay with what we've got here? There's something, Sophia, doing okay? All right. Now this is a section 7.2 problem. We got to figure out how we're going to integrate this. Now, what I see is we got this one lone secant of theta term hanging out there. If I'm going to make a u substitution with secant of theta, then what am I going to need? What's the du term going to look like? What's it going to have?
Secant theta, tangent theta?
Yeah, it's going to have a secant of theta and a tangent of theta. So I want to see if I can't rearrange this to split off a secant of theta and a tangent of theta. So let's try that. If I wanted to, I could rewrite this as tangent squared of theta times tangent of theta, secant of theta, d theta. There you go. Now I've got this split off, but that's a tangent of theta. This is the du term for secant of theta. So that's my du term. This is the du term for what u term? Well, it's u equals secant of theta. That's what that's implied. So that means I got to mess around with that tangent of theta. So I got to play with this. Replace. What am I going to replace tangent squared of theta with?
Secant squared theta minus 1.
Nice. Nice. So I need to move on to another sheet here. I want to keep that one around. You're going to want to keep that one around on your homework just for convenience sake. So I think that was Clyde maybe. So that's going to be secant squared of theta minus 1 times tangent of theta times secant of theta times d theta. Whew. Man, get out the oxygen bottle, man. This is a long one. We've set ourselves up for the following u substitution. So u is going to equal, let's see, secant of theta. And let's just jump to the chase. Du is going to be secant of theta, tangent of theta, d theta. So, all right, looking good there. This is a nice, easy substitution, straightforward. 27 times, let's see, it's going to be u squared minus 1 du. So 27 times 1/3 u cubed minus 1 plus your constant. And I'll distribute that 27 because I can get rid of that 1/3. So I end up with 9 u.
That would be minus u, right?
Yeah, it would be minus u. Thank you. So it's going to be 9 u cubed minus 27u plus a constant. And let's go back a little bit. That's going to be 9 times the secant of theta cubed minus 27 times the secant of theta plus your constant. But remember, and this goes back like 10 minutes now, remember way back at the original problem? We're trying to find an antiderivative in terms of x. That's not looking like x's right now. I can't differentiate that and get what I started with. So if you're like, wait a minute, that doesn't look right, good on you, because it's not right yet. We're not finished. What we have to do at this point is we have to look back at our triangle. And let me just kind of copy it over to here, just for convenience sake, because we're going to want to refer to it. So, I'll just do it here. So we had an x, 3, and a square root of x squared plus 9. This was our theta, that's our angle. But now we can find substitutions for these things. In particular, I want to know what the secant of theta is. Now, if you're looking at that going, oh man, see, you're really pushing it, Jeff. Secant of theta, that goes back a ways. Secant of theta is 1 over the cosine of theta, if that helps out. So it's basically the reciprocal of the cosine. And when you look back at SOHCAHTOA, the cosine was the adjacent over the hypotenuse. So what are we going to have for its reciprocal? Hypotenuse over the adjacent. So take a look at your triangle here. What's the hypotenuse? What's the adjacent side? Square root of x squared plus 9 over 3. So that's the secant of theta. Now we've got to feed that into our answers up here. But are we okay with where we got the secant of theta? Got a couple nods. A little bit of unease and uncomfort. I can understand that. But secant is just the hypotenuse over the opposite, or excuse me, over the adjacent. So there we go. If I fit that back in here, I get 9 times this cubed. And let's see, that's going to be square root of x squared plus 9 over 3 cubed minus 27 square root of x squared plus 9 over 3. Do me a favor. Don't finish it here. There's one more thing I want. Plus c. I'd really feel bad if I took off a point after all that beautiful work. Now, if you cube this out, there's going to be a 3 that'll cancel into that. So we'll end up with 3, and let me just call this x squared plus 9 to the 3/2 power. Actually, you know what? No, if I cube that, that's going to be a 27. So I'm just going to put the 3 in the denominator. My bad. So over 3 minus the 27 and the 3. Those are going to cancel. X squared plus 9 to the 1/2 plus c. You could, if you wanted, factor out x squared plus 9 to the 1/2 power and keep on playing around with this. I don't think it's going to get a lot more pretty. We're going to call it a done day here. Now, if you end up with something that's equivalent to my solution or the WebAssign solution, you should get full credit. Sometimes it's kind of hard to show that two solutions are equivalent. but I'll look at your work when we do these things. Whew. All right. It's like, what, 15, 20 minutes for one problem? Man, you guys are going to have a lot of fun this week. It was a lot here. There's a lot going on. Let's just kind of look back and do an overview of these types of problems. Your first job, when you recognize that, okay, this has got one of those square roots, this is not going to be an easy U substitution, is to figure out which one of these is going to simplify our integrand the nicest and make that X substitution, that trigonometric substitution. Now we did that one here. When we're done figuring out what our substitutions are going to look like, then we drew a triangle that represented our substitution. What was the double check that we chose the right trig substitution? What was our little thing like, oh yeah, this is the right one? How did we know? Say again? Not SOHCAHTOA. Yes. This term, the term in your integrand, should appear as one of the sides of your triangle. If it doesn't, you've chosen the wrong one. Stop. These are like really long problems. You don't want to get all the way down here and all of a sudden find out, wait a minute, I can't integrate this. I mean, something's going wrong. It's an awful lot of time to waste. So draw your triangle first. Make sure it matches here. And if it does, great. At least you can continue. Syed's like, oh man, my head is spinning. All right, I feel for you. Then we did our trig substitution. There's a lot of algebra and trigonometry that we did here to simplify this. We got down to here, and then we rearranged things so that we could make a U substitution. This is yet another substitution that we did. Once we had our U substitution, then we found the antiderivative, put it back in terms of theta, and then had to go back and figure out it in terms of x. Now there's one last thing I'll say here, and I see this on the test a lot. People do a lot of hard work, and bless them, I appreciate their effort. But if you did a lot of hard work on a problem like this, and you end up with an answer of equals 3x to the 3/2 plus x plus c. Why is that screaming out that it's wrong? What has to be true about this function here? What's an easy way to check your work? If you differentiate it, you should get the integrand, right? And I guess what I'm saying in a long-winded way is that this function here should be able to differentiate and get this thing here. You're not going to get a nice, easy, friendly polynomial. If you get something that looks too easy, it's wrong. It's just going to end up being kind of a mess, all right? There's no way about it. And so when I see people give me answers like this, I'm like, yeah, but you can check in your head that this won't differentiate to this. If it looks too easy and if it doesn't differentiate to this, it's wrong. Go back and take a look, see if you can't fix it. Or at least write me a note on your test saying, yeah, there's something wrong here. I don't know what it is. You'll probably get more pity points if you do that than you give me an answer that's just patently wrong, like a negative volume or negative length there. All right. Let's see here. All right. Let's do another one. That's probably all we'll have time for, to be honest. So it looks like we'll be doing these again on Thursday. Man, lucky you. All right. Well, I guess we can just move to B, right? Wow, look at these. These go up to H and I and J. Man, was I overprepared. Okay. Kind of a fun one that you can maybe play around with for yourself when you're done is this one. Now this one, I've done a lot of the work here for you. You can kind of look and see if you can't fill in some of the details. Although, in all honesty, yeah, I don't know. That one works. Yeah, that one works. Yeah. So your goal is to say, well, why can you go from here to here? All right, well, you've made the appropriate trig substitution. And then you use another trig identity, and then you can take the square root of that. So work your way through this. See if you can't figure out what justifies each step. That's not a bad way to go. I did hope to do that in class. All right, so example B. The integral of x squared over the square root of 9 minus x squared dx. Okay. Once again, we got to decide, well, which one of these trig substitutions are we going to do? Which one looks like it fits, A, B, or C? Or excuse me, A, 1, 2, or 3? Number 1? How come it's not number 3? I mean, both of these look pretty much the same. How come it's not number 3? Yeah. Here you've got your variable first and the constant second. Here you've got your constant first and your variable second. That's the form of this one. So our u substitution, well, let's see, we'll regard that as 3 squared. So our substitution is going to be a times sine of theta, or in other words, 3 times sine of theta. So x equals 3 times the sine of theta.
So is that x supposed to be squared on top?
Is it? Take a look. Yeah, you're right, it is. You know what? That's a great question. If it wasn't, then this would be a lot easier of a problem. Can anyone tell me why? If that wasn't squared there, what would you do? Suppose you had, this is a nice little brief aside, if I had the integral of x square root of 9 minus x squared dx, that one, you should probably be happy to see that one on an exam. Why is that one a lot easier? Yeah. What should be catching your attention is that you've got a second degree term. When you differentiate a second degree term, you got a first degree term. This would just be a really quick u substitution problem. That's all you need to do on that one. And let me be clear about something. I'm not going to ask that you do it the harder way if there's an easier way to do it. If you find an easier way to do it, go ahead. No problem on that one. All right, let's finish up our substitution for x is 3 sine of theta. That means dx. I need a dx term. Curtis, what do we got for dx? If you differentiate this with respect to theta, what are we going to get? We'll do it. Let's see. Let's just do derivative of x with respect to theta. What do we get for dx? 3 cosine of theta. And then we're going to solve for dx. So multiply both sides by d theta. dx equals 3 cosine of theta d theta. Great. Now you can make your substitution. Before we do our substitution, let's deal with our triangle. So our triangles, let's see, and just sketch one in here. Draw yourself a nice little right triangle. Draw on a theta. So here's our theta. Let's solve this for sine of theta. That's going to mean x over 3 equals the sine of theta. Now go back and revisit your SOHCAHTOA stuff. See if you can't label the sides correctly. What would they be? At least start out with the first 2 sides. Oh, not again. Wake up, wake up. There we go. Don't know what's going on with that. What could these sides be? What do we got?
X is on the right side. And
All right.
3 is the hypotenuse.
3 is the hypotenuse. Nice. Now, if you solve for this side, you know, call it A or call it B or whatever you want, you're going to have to use the Pythagorean theorem, right? So let's call it B for the moment. You're going to have B squared plus X squared equals 3 squared. Or if you solve for X, oh, guess what? You get X is equal to 9 minus, excuse me, yeah. I guess I should put B here maybe. B is equal to 9 minus the square root of 3. So that's going to be this side here, which is what we expected, right? We expected this to be some function that paralleled this right here. 9 minus x squared. This is your double check of your work. Okay, lots of substitution, a little bit of work here to do as well. Let's see what this looks like. In the numerator, I'm going to throw in an x and replace that by 3 sine of theta. So 3 sine of theta squared. In the denominator, it's going to be 9 minus 3 sine of theta squared. And then dx is going to get replaced by 3 cosine of theta d theta. 3 cosine of theta d theta. Everything's in terms of theta. We got rid of the x. You shouldn't have an integral with mixed variables in it. Should all be x's or all be thetas or whatever. You shouldn't have something that's all mixed up. All right. The 3 and the 3 give me a 9. So it's going to be 9 sine squared of theta. I'm going to bring the cosine of theta d theta up in the numerator. Cosine of theta d theta in the numerator.
Wouldn't that be a 27 in front? 'Cause of
Yeah, you're right. 27. Thank you. So 27 there, and I'm missing something here. Where's my... Oh, here it is. Thank you. So let's take care of a couple things. That, and yeah, that'd be a 27. Don't worry. If you make a mistake like that on the test, I'll simply mark it wrong. All right. In the denominator, this term is going to simplify. That's going to simplify as 9 sine squared of theta. And it's going to be really 9 times 1 minus sine squared of theta. Now I'm doing a couple things. I'm squaring that out and I'm factoring out the 9. Why? What happens to 1 minus sine squared of theta? What's the nice thing I can do here? Yeah, cosine squared. So this is really 9 times cosine squared of theta. And square root of 9 cosine squared of theta becomes what? 3 cosine theta. Thank you. So 27 sine squared of theta cosine of theta d theta over 3 cosine of theta. Whew. And wow, that thing actually is going to work out okay. How's it going to work out okay? Well, we get a couple cancellations here, right? The 3 cosine of theta should cancel. The cosine of theta is going to cancel, and then the 3 will cancel. That's going to leave us with the integral of 9 times the integral of sine squared of theta d theta. And okay. Any suggestions as to what to do with 9 sine squared of theta? Oh, the power reduction formula. Good choice. 1 minus cosine of 2 theta over 2 d theta. Bring the 2 out in front. 9 over 2. The integral of 1 minus cosine of 2 theta d theta. 9/2 theta minus, so I don't remember what we're going to get here.
1/2 sine.
Yep. Instead of differentiating, which would cause a times by 2, you're going to integrate, which is going to cause a divide by 2, or multiply by 1/2. So 1/2 sine of 2 theta plus or constant. Whew. This one's a little bit more messy than the previous one in one regard here at the end. At the end here, we're going to need to replace this with a trig identity. So it's going to be 9/2 times theta minus half of sine of 2 theta is the same thing as sine of theta cosine of theta plus a constant. We're going to go back and look at our triangle here now. Remember, this is probably going to end up to be something a little bit on the messy side, and that's okay. Let's take a look at sine of theta. Sine of theta we already know. Sine of theta we solved for earlier. That's just going to be x over 3. What about cosine of theta? Adjacent over hypotenuse. That's going to be square root of 9 minus x squared over 3. And now we need one more. We need an expression for theta, because we need to substitute something in for theta. And I don't have anything directly there, but I can get something from right here. How do you solve this for theta?
Inverse sine.
Ah, thank you so much. Inverse sine. So it's going to mean theta is the inverse sine of x over 3. And now I've got everything I need to plug this back in. 9/2 inverse sine of x over 3. Oops, not a minus. It should be a minus, not a plus. Minus x over 3 times square root of 9 minus x squared over 3 plus a c. I'm not going to bother to simplify that. If you got this far in a problem like this on a test, my inner child would be doing somersaults. I'd be really, really happy there. I'm not worried about the 3 in the denominator. 3 times 3 is 9. Okay. Whew. Tough one. Comments or questions? Good. All right. Have a good afternoon and see ya.